Good afternoon, everybody. Just 1 second here and we can get moving. So I am still working on your tests. Some of you have grades in now, some of you do not. Unfortunately, the drawing pad that I got from the college, which would allow me to annotate your things directly, is a piece of shit. I should have seen that coming. In the past, I've printed everything, marked them up by hand, then pulled staples out and scanned. That takes hours and hours of just staple pulling and scanning. So I was thinking this pad would save me time, but it is quite the contrary. The thing is horrible. And some of you may have noticed that the comments that you're seeing on there are a mixture of typed comments and drawn comments, and the drawing pad is, again, just awful. So I'm still working on finding a way to do this nicely. Which means it's taking a little bit longer than I anticipated. But my goal is to get everybody's stuff fully graded today, 1 week within 1 week of the test day is always my goal. But I know that some of you are still waiting, and to those of you that are still waiting, I'm sorry, I'll ask you to be patient, but we're almost there. So I promise we'll be there very soon. You'll always have your grades from me within 1 week of when you turn them in. That is the promise I make to you. Today, we're going to continue our discussion of polynomials. So last time, we learned how to complete the square. We reminded ourselves all the facts that we know of quadratic functions. We saw how to prove the quadratic formula by completing the square, and also how we can use that method of completing the square to go from the ax squared plus bx plus c form into the vertex form, the a times x minus h squared plus k, which is the nicer form to graph a quadratic. Hopefully all of that was review, except for completing the square. Then we talked a little bit about end behavior. So last time, I'll give you a quick recap. We talked about how to complete the square. We talked about the forms of a quadratic. Ax squared plus bx plus c, and a times x minus h squared plus k. So I will get to your question here in just a second, Lily, but if the degree is even, it's not the even or oddness of the coefficient, it's whether the lead coefficient is positive or negative. If the degree is even and the lead coefficient is positive, then as x goes to negative infinity or positive infinity, y would go to positive infinity. We talked about the definition of a polynomial. Which is an x to the n plus an minus 1, x to the n minus 1 plus an minus 2, x to the n minus 2, all the way down to a1x plus a0. Remember, the degree of a polynomial is the largest power of x that shows up in the expression. The number that is attached to x to the n is called the lead coefficient. And the term that doesn't have an x attached to it is called the constant term. And then a few other little things, but we talked about end behavior. So I'll go ahead and give you a quick sketch here. I'm not going to spend a lot of time. If you want the details, go see the lecture from Monday. So if the guy's pointing up on both sides, this is a positive lead coefficient. And even degree. The arrows pointing down on both sides corresponds to a negative lead coefficient. And an even degree. If the arrow is going down on the left and up on the right, then this is a positive lead coefficient. And an odd degree and if you flip that picture over, then that is a negative lead coefficient and odd degree. And we had that goes to notation. So I want to work a few specific examples today. This is forms of quadratic. So you're sort of, this is normally what I would call standard form, and this is normally what I would call vertex form. But your book calls this the standard form and doesn't give a name to this. It's very frustrating. But this is the guy where you can read off the vertex as h comma k. This is the guy that you would normally have if you wanted to factor or if you wanted to plug into the quadratic formula, something like that. So I am counting on you guys remembering what you learned from college algebra or your previous algebra classes when it comes to quadratic functions. I'm not going to spend a lot of time there. Oh shit, I think this might be the vet that I've been dealing with and things have been bad here. I'm going to ask you guys to hold for just 1 minute. I'm so sorry. Sorry about that, guys. I really appreciate your patience with me there. I normally would never do this, but I'm going to take a moment of class time here to say, fuck the Millhopper vets. My dog started bleeding from his nose back in early August, and I paid them an extraordinary amount of money to do radiographs and send the radiographs out for a specialist to analyze them. They assured me they would have those results in 5 days. That was August 3rd. I called them probably 20 times between then and now, and only today, after screaming at them no small amount, did they actually say they have the result from the radiologist. They've had it since September 3rd. Never contacted me, and meanwhile my dog is bleeding from his nose and slowly dying from cancer. So I hate them. They used to be very good before they were taken over by Banfield, which is a large corporation. So if you have pets and you live in the Gainesville area, stay well away from Millhopper Vet. They used to have a good reputation. Their Google reviews are good. They used to be good, but they are not anymore. All right, thank you. Now, where were we? Polynomials, definition of polynomial, end behavior for polynomials. So I'd like to look at an example or two of specific polynomials and their end behavior, but then I want to talk about the connection between factors and roots. So let's do that. Example first, right? Okay. So let's describe the end behavior of p of x equals negative 3x to the 4 minus 7x cubed plus 2x minus 5, whatever. More, I'm just being silly there, more polynomials. We're playing around with polynomials a little bit more. So I want to describe the end behavior of this guy. And to do that, I need two things. I need to know the degree, and I need to know the lead coefficient. So here the degree is 4, because the largest power of x that shows up anywhere is x to the 4. And the lead coefficient that's negative 3. So because the degree is even and the lead coefficient is negative, I know that the picture, I don't have a clue what this thing does in between, all sorts of stuff. Could be anything in here. I don't have any idea myself, but I know that on both sides, eventually the arrows will go down, just like negative x squared or negative x to the 4 would. So this means that in the goes to notation, we would say as x goes to negative infinity, as we wander very, very far in this direction, the y values go to negative infinity as well. That's describing this arrow. As we wander off to the left, eventually we go down. And as x goes to positive infinity, y goes to negative infinity. That's describing this guy. It says as we go very, very far to the right in our x values, we'll be ending up going down eventually. Again, just like negative x squared or negative x to the 4. If I gave you the polynomial x minus x cubed, here we have to think maybe just a little bit more than in the previous guy, because he's not in this like regular order that you see in the definition. You can put him into that regular order as negative x cubed plus x. This is a degree 3 polynomial, because the largest power of x I see anywhere is 3, and the lead coefficient is negative 1, because this negative attached to my x cubed is the same as negative 1 times x cubed. plus x. So here the degree is odd. The lead coefficient is again negative. So the picture I would associate with this is the odd negative picture from the previous page, which looks like this. And again, I can't, based on what we've seen so far, say what happens in between. But I know that on the left, the arrow goes up, and on the right, the arrow goes down. The arrow going up on the left in the goes to notation says as x goes to negative infinity, this is as we wander further and further and further to the left, the y values will eventually go up. So y eventually goes to plus infinity. That's describing the arrow on the left here. And also, as x goes to positive infinity, y in this case goes to negative infinity. Okay. So this is really everything you need to know about end behavior, and this is as much as you'll need to do with it. I might give you a polynomial and ask for the picture or for the goes to information. I could give you the picture and ask you, is the degree even or odd? Is the coefficient out front positive or negative? Or I could give you the goes to notation and ask you for either the picture or the information about the degree and the lead coefficient. These three things are all equivalent. So if you know one, you should be able to infer the other two from them. Question on the games we played here? Any uncertainty about how I drew those pictures or wrote down those goes to notation bits? Okay then. The sort of mystery here is what's going on in the middle, right? All this stuff. I would like to know what's going on in here. I want to be able to draw a good graph of these polynomials. That is the end goal for this section. I give you something like this, and you give me not just this thing where the middle is unknown, but you give me the whole graph. And you could always get there by plotting points. If you plug in a shitload of x values here, eventually with enough x values, you'll get a good picture for the graph, but it can be horrendously complicated to do. So what we need to start doing is finding connections between the algebra structure of the polynomial and the geometric structure of the graph. The first step along the way to doing that is to learn a few facts about polynomials. Polynomials are continuous. Everywhere on negative infinity to infinity, which means you can draw the graph without lifting your pencil. The mathematical word for that is connected, right? No breaks, no holes, no jumps, no asymptotes. So if I hand you a graph and I ask you, could this be the graph of a polynomial? Your first thought should be, is that graph a single connected piece? If it is not a single connected piece, then it could not possibly be the graph of a polynomial. And smoothness is the next criterion. So polynomials are all smooth. Everywhere on negative infinity to infinity. This means there are no hard corners. No cusps or points. I'll say pointy bits, so we don't confuse ourselves with the idea of a point like 5, 3. So again, if I hand you a graph and I ask, could this be the graph of a polynomial? If it has any like hard corners, like the absolute value graph, or it has any pointy cusps, like x to the 2/3, those could not be polynomials. So continuous and smooth, that's two big restrictions. The next thing I want to talk about is the connection between factors and graphs. Okay, yeah, so a discontinuity, while we're here, yeah. Let's look at a picture. So this could not be the graph of a polynomial, whether this is filled in or not. This is not continuous. Also, a failure to be continuous could look a few different ways. You could have a vertical asymptote, right? Something like this. If you've got any sort of business like that going on, automatically not continuous, so not polynomial. The other sort of failure of continuity is just a hole. So if I give you something like this, also not continuous. A cusp, or a failure of the smoothness condition, would be something like this. Or kind of similar, but a little bit different. Something like this. This is called a cusp. Right, so none of these could be the graph of a polynomial. A cusp is a place where the graph is very pointy. So like extra super duper not smooth, rather than just like sharp corner not smooth, pointy sharp corner not smooth. This object here is called a cusp. Some examples of things that look like this are like the absolute value of x. Some things that look like this are like x to the 2/3 power. Those have those sort of pointy things. These two sorts of things, like this or like this, you'll see these coming from rational functions, like a polynomial divided by another polynomial. And then places where the bottom is 0 can give you a vertical asymptote or a hole, depending on what's going on. And then stuff like this, you'll mostly see from piecewise functions. But certainly if I give you a graph that has any of these features, not a polynomial. And that's all well and good. These are tools for ruling out polynomials. But what about things for ruling in? So how can you start actually drawing the graph? Well, for that, we need a handful of theorems. First one is, if x minus r is a factor of the polynomial p of x, then p of r is equal to 0, i.e. the point r comma 0 is an x-intercept, or root of p of x. So x-intercepts always come from factors. Another word for x-intercept is root or 0. I don't like to use the word solution there because solutions are things that equations have. Polynomials are functions, not equations. You set a polynomial equal to 0, then you've got a solution, but we discuss roots in other settings also. So roots or x-intercepts, whatever you want to call them, places where the function is 0, those come from factors. And this is an if and only if. So not only if this is a factor, then this is a root, but also the converse is true. So in other words, x minus r is a factor if and only if p of r equals 0, i.e. r is a root. This is intuitively true in the one direction. If x minus r is a factor, then when you plug in r for x, you'll have this factor being 0, and 0 times anything is 0. The converse is a little bit harder to prove, and it's a consequence of the fundamental theorem of algebra, or if you like, a consequence of the division algorithm, which is the next thing we're going to talk about. Before I talk about that, though, I want to define something, and that's multiplicity. A number r is called a root of multiplicity m for the polynomial p of x means that x minus r to the m is a factor of p of x. And the multiplicity of a root tells you how the graph looks near the corresponding x-intercept. So remember, our goal here is to get to a place where we can draw graphs of these functions. So a root of multiplicity 2 will look like this. A root of multiplicity 1 will just look like a line crossing the x-axis locally. A root of multiplicity 3 will look something like this. A root of multiplicity 1, like I said, just kind of looks like a line crossing the x-axis. This is what's called local behavior. Our root of multiplicity, let's see, we got 1, 2, 3, 4. Looks a lot like a root of multiplicity 2, only it's flatter. Oh, not 2, 4. A root of multiplicity 5 looks like a root of multiplicity 3, only flatter. And that's kind of the pattern. What you'll notice is that the graph of P of X will cross the x-axis at a root of odd multiplicity and will bounce off the x-axis at a root of even multiplicity. Okay. So I've given you quite a lot to digest just here. So before I give you any more, I just want to play around with these things and see how well we've internalized them. So every x-intercept or every root comes from a factor, and every factor gives a root. The shape of the graph near that root, which we call local behavior, the behavior nearby or locally, is determined by the multiplicity of the factor from which the root comes. I can show you some examples of that, but before I do that even, I want to just show some examples using this theorem. Any questions on the things that are written here, just what's being said and what it means? So like right here, you see the graph, it doesn't cross the x-axis. It just comes down and touches the x-axis, then turns around and runs away the other direction. That is a bounce. This is a bounce. This is also a bounce. This is a cross because the graph goes from beneath the x-axis to above the x-axis. This is also a cross because the graph goes from one side of the x-axis to another. So if the graph doesn't cross the x-axis but just touches it and then runs back the other way, that's a bounce. And if the graph does cross the x-axis, that's a cross. So let's address these, let's address them through some examples. Can we find a polynomial with integer coefficients? Remember, integer means whole number. Coefficients are the numbers that multiply the various powers of x, which has roots at, let's say, -5, 1, and 3/2. Fuck it, let's also say and 7. Well, according to our theorem, roots come from factors. So for every one of these roots, there needs to be a factor. Yeah, that's exactly correct, Lily. So the x equals -5 being a root means x minus -5 has to be a factor. One being a root means x minus 1 has to be a factor. 3/2 being a root means x minus 3/2 has to be a factor. And 7 being a root means x minus 7 has to be a factor. And factors being what they are, this is your polynomial, right? Now, does this have integer coefficients? Well, like you said, this is x plus 5 times x minus 1 times, this would be x minus 3/2. Now this is x minus 7. If I multiplied all this out, there are going to be some non-integer coefficients, right? Because of this 3/2. So we'd say, but this isn't going to have integer coefficients. So is there another factor I could have used here that would give me that root? All the other factors are good. The x plus 5 is fine. The x minus 1, those give me the roots at -5 and 1. This guy, I could instead use 2x minus 3. Notice that he is also 0 when x is equal to 3/2. In other words, if you multiplied through this whole polynomial by 2, you would get the polynomial that I requested. So this is the guy we want. And we could multiply all of this out. What would be the degree of this polynomial? I think 4, right? Because each of those factors is a multiplicity 1 factor. So each factor will increase the degree by 1. So if I multiplied all of this out, what would my lead coefficient be?
(2x).
2. Good. Yeah, the lead term would be 2x to the 4, and the lead coefficient would be 2. So we can actually draw a reasonable picture of this graph just from the information we have. Check this out. I know I have x-intercepts at -5, 1, 3/2, which is 1.5, and 7. Also, I know the degree and lead coefficient. The degree is 4, because if I multiplied all this shit out, and that's an awful lot of foiling, I don't actually want to do that. I know that I would have at the very front 2x to the 4. So the lead coefficient is 2. So the degree here is even, and the lead coefficient is positive. So I know that my arrow on the left is going to go up and my arrow on the right is going to go up because that's the end behavior. And then each one of these guys is multiplicity 1. So each one of these guys, the local behavior is going to look like just a cross. And here, since I'm starting from up, as I come in, if I'm going to cross here, I got to cross like that. Which means when I come back here, I've got to cross like that. When I come back here, I've got to cross like that. And when I come back here, I've got to cross like that. So if you connect these pieces together, it's got to look something like this. That's the only possibility. So if you have the factored form, then you can draw a nice graph. You figure out the degree and the lead coefficient to get the end behavior. Then you figure out the local behavior using the multiplicities of the roots. And then you just connect those pieces.
Wait, I have a question.
Yeah.
In order for it to bounce off the x-axis or go through it, does the degree have to be even, or does the root have to be even?
The root has to be of even multiplicity to bounce. So I'll show you another example in just a minute where the multiplicities are not all 1, and we'll attack those issues there. Billy asked a good question. How do I know at each root whether it crosses like this or like this? That's where the end behavior comes in. So you start at the left all the way over here. If this arrow points up, then you know it has to come down like this, which means that when you get to here, it has to cross like that. Couldn't cross the other way because the only way it could cross the other way is if it was coming from down here. So first you fill in your end behavior. Then you imagine going in and filling the local behavior, and you know which direction to cross based on how the end behavior starts on the far left. And then you just chase. Okay, up here I came in from positive. So here I had to go from positive to negative because it's a cross and I'm coming in from above. Couldn't be negative to positive, had to be positive to negative because I'm starting out above. Crossing like this puts me down below. So when I get to the root at 1, it has to go a negative to positive cross like this. Couldn't be the other way because I would have to be coming in from above for that to happen. And we just follow that pattern as we go through the rest of it. Cool stuff, right? Let's try another example. Now I'm going to specify some multiplicities. So find and sketch a polynomial with integer coefficients having roots, say, -3 of multiplicity 2, 0 of multiplicity 1, 2 of multiplicity 3. So each root gives me a factor. X minus -3 needs to be a factor. And the multiplicity there is 2. X minus 0 needs to be a factor from this root, and the multiplicity is 1. And x minus 2 needs to be a factor of multiplicity 3. So this is x plus 3 squared times x times x minus 2 cubed. If I multiplied all of this out, this guy's lead term, if I FOIL him, is x squared. This is x squared plus 6x plus 9. This would make that x cubed plus 6x squared plus 9x. And then when I multiply all this shit out, the lead term from this is x cubed. So here I would have x, these guys give me lead term x cubed. This guy also has lead term x cubed. So the lead term for this polynomial would be 1x to the 6. This looks like 1 times x to the 6 plus lower order stuff. So the degree is 6, which again is even, and the lead coefficient is 1, which is positive. So the end behavior here is the same as the end behavior in our previous example. Up on both sides. I've got a root at -3. I've got a root at 0. I've got a root at +2. And then the root at -3 is an even multiplicity root. So it either looks like this or like this. It's got to be a bounce. And the question is it positive to positive bounce or negative to negative bounce? Based on the, okay, let's take a pause then. Let's pause for just a second. How did I get the degree? A nice fact, the degree is always the sum of the multiplicities. That's the easiest way. But you could also think about multiplying all this out. If I multiplied this out, the highest order term would be an x squared. Here I've got another factor of x, and then here the highest order term would be x cubed. So the lead term would look like x squared times x cubed, which is x to the 6. Or I could add the multiplicities. 2 plus 1 plus 3 is 6. So this fact is nice. It comes immediately from the definition of multiplicity and basic algebra rules, but it can save you time to think about it that way. The other question might have been, how do we know that 1 is the lead coefficient? So is the lead coefficient 1 because all the x have 1 in front of them? Yes. Yes, the lead coefficient, the lead term always comes from the product of the individual lead terms. So the lead term in this piece is 1x squared. The lead term here is just 1x, and the lead term here is 1x cubed. So if you multiply all those lead terms together, you'll get the lead term of the polynomial overall, which is 1x to the 6. Right. Yeah, so if this was a 2x, then the lead term would be 2x to the 6. Or if this was 3x plus 9, then the lead term would be 3x to the 6, and so on. All right, everybody comfy up to this stage, where we have the degree and the lead coefficient?
Yeah.
Because from there, we can draw our graph. Like we said, the multiplicity at -3 is 2, so it's got to bounce. And the question is, does it go positive to positive or negative to negative? Because my end behavior on the far left is positive, it has to be positive to positive. If you zoom in on this piece, it's going to look like x squared. The root at 0 is of multiplicity 1. So he has to be a cross. It's either going to be like this or like this. Since I leave this root positive, I have to arrive at this root positive. So it has to cross like this. The root at 2 is of multiplicity 3. So he's going to look, remember from our shape thing there, he's going to look either like this or like this. Because it's a multiplicity 3 root, the local shape there is this kind of S squiggly shape, and it's either going negative to positive or positive to negative. Well, I leave from here going down, so I have to arrive here, negative. So yep, it's got to be something like this. And now that I have the end behavior and the local behavior near the roots, I can connect the bits. And I connect them smoothly because polynomial graphs are always smooth. And there again is a reasonable sketch of this polynomial. Now, do I know how tall this hill is or how deep this valley is? Do I know this max or this min? No. No, I don't. You're gonna have to wait for calculus to learn that. But this has the right number of maxes and mins. That's a big deal on its own. Because I have this graph based on the end behavior and local behavior near the roots, I can say for sure how many times this polynomial turns around. So how many mins or maxes it has. And also I have the relative placement of those mins and maxes. I know that there has to be a max between -3 and 0. I know that there has to be a min between 0 and 2. Basically, polynomials are very rigid. They're like glass. Once you have a little, or like a crystal, that's a better way to think. It's like a crystal structure. Once you have the seed, the little crystal seed, if you've ever grown crystals, the entire structure grows on that automatically. It's set by the seed. The roots are the seed. The roots, with their multiplicity and local behavior, determine the shape of the graph overall. And then the end behavior, you could flip this whole picture upside down just by slapping a -1 out front here. So the end behavior just comes from the degree and the sign of the lead coefficient. Once you have the local behavior and the end behavior, you have the essential behavior of the polynomial and can draw a very nice graph. It's beautiful. It's remarkable how much information you can get from the factored form of a polynomial. Now the big question, how the fuck do you get the factored form of the polynomial? That, ladies and gentlemen, is the hard part. And for that, we need to learn a handful of theorems. The first of which is just called the division algorithm. So I'm going to part with you today showing you how to divide two polynomials. Yeah, if you know the local behavior for multiplicities 1, 2, 3, and 4, you're in good shape. Really just 1 and 2 are enough to give you the right number of mins and maxes. I like to teach 1, 2, 3, and 4 because this kind of squiggly shape can throw people off if they're not expecting it. But yeah, I won't hit you with anything that you need to know higher end behavior or local behaviors for. And the truth is that the other local behaviors are all just like power functions. So if it's odd, it will always be this kind of S shape. And if it's even, it will always be a kind of U shape. And then the higher the power, the flatter the curve is, the more it's squished down onto the x-axis. So dividing polynomials. And the remainder theorem. I'm going to give you the theorem first. P of C is always equal to, this is for any polynomial, the remainder when P of X is divided by X minus C. This theorem is kind of like magic. So if you have to compute the value of a polynomial at some number and you don't want to just plug that number in, maybe it's too hard, maybe the numbers get big when you do that, you can instead divide the polynomial by the factor X minus C. Think about it with me for a little bit. If X minus C, this chunk, divides neatly into P of X, that means that X minus C was a factor of P of X. And so the remainder when you divide would be 0. Oh, well, if the remainder is 0 and the remainder is equal to P of C, then P of C has to be 0. In other words, if this is a factor, then P of C is 0. We know that. We know that factors and roots come together. It also works when P of C is not 0. So let me show you how to divide some polynomials. The division algorithm. There are some great videos on YouTube by Patrick JMT, where you can watch him do this with lots of other polynomials. Let me grab, I think I have an example or two in your homework that I can use here. If I haven't, then I'll stop the class here, but I think I did give you 1 or 2 of these to play with this week. I appreciate you guys being patient. I know that call took a second. Okay, so identifying these shapes, that's all well and good. Getting the shape from that stuff. Where's the division stuff? Did I hit you with any of these? Oh, maybe not. Yeah, no. Yeah, okay. Value of C, consider the following. Show that this is a 0. Right, all right. So let's do some division. Here, the factor theorem was the theorem I gave you a minute ago, saying that X minus C is a factor if and only if P of C is 0. Let's go ahead and try to divide x cubed minus 3x squared plus 3x minus 9 by x minus 3. Yeah, I think I banished the division into next week's. So I guess you don't need it. Yeah, okay, fuck it. This is a fine place to stop for today. And I've already pushed you guys 7 minutes over time, so I'll stop here. Next week, we're going to talk about how to divide polynomials. So this is where we will pick it up next time. You don't actually need this theorem for this week's homework. The heaviest theorem that I ask you to employ is this one, which is called the factor theorem, right? So yeah, we'll leave it there for this week. And then next Monday, I will start showing you guys how to divide polynomials. I do want to suggest that you look at a video or two beforehand because it will help you. We're going to learn both long division and synthetic division, so I'll paste these into chat. Here's one. Long division is what I will teach you first, and it always works. Synthetic division works in some special cases and is much, much faster. So next week, that's where we're going to start. If you want to get ahead, take a look at those. Otherwise, I hope you guys have a lovely rest of your week, and I will see you on Monday. I will add these to the modules page. And that way you can take a look at them there. But yep, that's where I'm going to stop it for today. If you want to talk more, I do have an office hour, so I can meet you over there. All right, take care.
Thank you.
Of course.